Welcome to the second part of section 11.1 in AP Statistics. This is about match pairs testing and about the robustness of T. If at any time you need to pause for a moment, please don't hesitate to do so. I'm going to move fairly briskly through the material. If you want to watch a section again, or if you want to watch it when you're at home, all of those might be good ideas in helping you to understand the content. Today's lesson, once again, brought to you by the letter T. This guy, William S. Gossett, I flashed past him in the last lesson. He's actually one of the mathematicians who, in the early 20th century, developed the T procedure. That's his claim to fame, and we love him for it. Okay, so match pairs design. You've seen match pairs design before. We talked about it during the first semester of the course, and the idea is this. Subjects are matched together. And each treatment is given to one subject of the pair. So you and I are pairs, and they give me the placebo, and they give you the drug. Or they have an experiment where they want to see the effect of, like wearing a hat on your ability to run a foot race. So they'll have you run it once without a hat, and then they'll have you run it once with a hat, and so you'll be your own pair. That's the idea of a matched pairs design. We actually saw a matched pair in the last lesson, and that was with the sweetness loss. Remember, we had the problem where we were interested in the cola, and is the cola losing sweetness when it is refrigerated and stored? And so the pairs were, we took a measure of its sweetness before being stored and then after stored. And so the pair was the same batch of cola at two different times in its life. Here's an example. I'm calling it Smell You Later. It starts with this. It's known that listening to the right music improves test scores. You're told that listening to Mozart before you take the ACT or the SAT or whatever is going to improve your performance on that particular test. My brother once tried to put this into practice and ended up listening to Mozart for a half hour before he took the PSAT, except for that the first hour of the PSAT is all involved like bubbling your name on Scantron. So he did that really well, but he didn't say it really helped him on the test. Anyway, the long and the short of it is that the right music improves your cognitive abilities. The question of this problem is, could smelling the right odor have a similar effect? And here's how we run the experiment. We've got 21 subjects. Each one of them is going to take a paper and pencil maze. And what I mean by a maze is this. Imagine, I know you had one of these in elementary school. We'll imagine it's maybe slightly more difficult where you've got this little corridor and then you go this way, or there's the dead end, or maybe you went that way, or blah, 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 and uh-oh, there's the Minotaur right there waiting to catch you, and here's the start, and somewhere over here is the finish. Okay, so they're going to run one of those mazes. And what we're going to do is we're going to measure the time it takes for them to finish the maze. Here's the pairs. One time an individual is going to run it wearing a scented mask, and this scent is going to be something that we imagine will help with cognitive ability. And then the other time the individual is going to wear a mask, but it's not going to be scented. One thing we need to be careful with these matched pair experiments is that we randomize the order in which the two things take place. For instance, suppose it's the same maze, and it should be, then the fact that you've run the maze once already is going to make your second run a little faster. And so what we need to do is we need to randomize which mask is worn first, so that approximately half of the participants are going to wear the scented mask first, and roughly another 50% of them are going to use the unscented mask first. Let's imagine what this situation looks like. I'm going to draw it out a little bit. I think it would probably be useful for you to draw this same picture. Okay, so here's our data. We've got the scented data, unscented data, and then the scented data, and then we've got the differences. So for subject 1, let's suppose subject 1 takes 2 minutes with the unscented, and then takes 1 minute with the scented, which would suggest that the scented did help. We're going to subtract those, and we're going to get 1. So a positive number refers to something where the scented was to our benefit. Okay. Subject 2, on the other hand, let's suppose that it takes subject 2 3 minutes to use the unscented, and then 5 minutes with the scented. It takes longer. So this time 3 minus 5 is going to give us -2, and we get a negative number. And so that says, well, maybe the scented didn't really help, where here this suggests that the scented did. So that's what the data is going to look like. The upshot is that x of the difference is going to be equal to x of unscented minus x of scented. Okay, so what's the appropriate significance test in this case? Well, we don't know the standard deviation, so it's going to be a t procedure. Okay, our population is May's times. You want to be more specific, you can say difference in May's times. And the parameter is going to be the mean difference. And that means we need to talk about a null hypothesis and an alternative hypothesis. Well, once again, the null is always something that's easy to test. So that's going to be that the mean difference is 0. And that correlates to the idea that scent has no effect. On the other hand, our alternative hypothesis is that we think scent has an effect. In fact, we think that scent helps. And if scent helps, then the unscented time is going to be longer than the scented time, which means this is going to be positive. Here's the actual data. You can see that here's our unscented, here's our scented. We're subtracting them to get this number. Subtract to get this number. Subtract to get this number. One thing we might think about doing before we actually do any calculating is looking at, out of the 21, how many of them are positive? Because the positive are the ones that are going to suggest that scented works. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 out of 21 is not very many. So I'm already a little suspicious because of that data whether we're going to be able to reject this null hypothesis. Okay. So standard deviation, once again, we don't know, so we're going to use the t procedure. Okay, is it well designed? Yes, it's matched pairs, and we know that we've taken into account randomization. So it's a well-designed experiment. Is it normal? I threw the data into the calculator, and it's reasonably close to normal, so check. Here's another way we can think about it, and this is what the book does. Here's a stem plot, and you can see from the stem plot that we've got something that's fairly symmetrical with a mean somewhere in there. Now let's calculate our p-value. So we put all the data into the calculator. You don't need to for this one. And we get 9.567 seconds. So it is positive. But we got this really large sample standard deviation of 12.5479 seconds. And our number of samples is 21, which means our degrees of freedom is not going to be 21, it's going to be 1 less than 21, which gives us 20. So our t is equal to our test statistic, take away the null hypothesis. This is going to be null right here. And the null hypothesis says that there's no difference between scented and unscented, and so the differences will be 0 divided by 12.5479 over the square root of 21. And when you crunch that out, you end up with 0.349 as our t-score. Now, in order to interpret that t-score of 0.349, because what we want is the p-value, which is equal to the probability that t is larger than 0.349 just by chance if the mean actually is 0, if the null hypothesis is true.